Hello everyone, my name is Keiya Sakabe. Our presentation title is Gradient Descent for Unbounded Convex Functions on Hadamard Manifolds and its applications to scaling problems. In usual convex optimization, the objective function is bounded below. In this case, the optimization algorithms will converge to the minimizer of the function. This kind of problem is meaningful as the most basic problem of optimization theory. On the other hand, we consider unbounded convex optimization. If the objective function is unbounded below, the optimization algorithm will diverge. So you might think that this kind of problem is meaningless. However, we proved that the gradient descent for unbounded convex function converges to a specific point at infinity. Here's our main theorem. It states that the gradient norm will converge to the infimum of gradient norm on Holder manifold. And the gradient descent sequence converges to a specific point at infinity. And their properties are related in a single equation. And we would like to emphasize that this kind of convergence is new, even in the Euclidean case, and this has important applications in geometric invariant theory. Especially the limiting point corresponds to a destabilizing one-parameter subgroup. And we also characterize the gradient descent limit of operator scaling. A Hadamard manifold is a Riemannian manifold which is complete, simply connected, and which has non-positive sectional curvature. And the latter two properties are called cat0. The Euclidean space, the hyperbolic space, and the set of positive definite Hermitian matrices are examples of Hadamard manifolds. Hadamard manifolds have strong properties about geodesics. First, for any 2 points, there exists unique geodesic between them. And any geodesic can be extended infinitely, so we can consider the exponential map. The exponential map is a natural map from the tangent space to the original manifold. And exponential map at x of tu is defined as the point at the distance d along the geodesic toward u. And here u is a unit tangent vector. And the convexity is defined geodesically. More precisely, the function on the Hadamard manifolds is called convex if and only if this is convex along any geodesic. And the smoothness is defined likewise. And the gradient descent method on this kind of function is defined using the exponential map. And here, the step size should be 1/L or less. Indeed, in the bounded case, if we take the step size less than 1/L, then it is known that the sequence will converge to the optimum. Then we introduce boundary. Interestingly, this is a set of points at infinity. The cone topology is a compactification of the Hadamard manifold. And the set of points added during the compactification is called boundary. More precisely, we fix a point in the manifold. Then, any point in the manifold can be expressed as the exponential map at x0 of tu. Then we consider the limit of t to infinity. Then we obtain a point on the boundary. And from this relation, we can identify the boundary with the set of unit tangent vectors at x0. While this explanation depends on the x0, But please note that the concepts of count topology and the boundary itself are independent of X0. Next, we introduce the recession function, which is a strong tool to study unboundedness. For a convex function f, the recession function is defined as the f of exponential map of tu divided t and takes the limit of t to infinity. This is intuitively the increasing ratio of f at the infinity. And it is known that the recession function is defined on the boundary under this identification. The recession function is well known in the Euclidean convex analysis, and this is the generalization to the Hadamard manifolds. And you can easily observe that if the recession function has negative points, then the original convex function is unbounded below. And indeed, it is known that this condition is equivalent to the condition that the infimum of gradient norm is positive, and that under this condition, recession function has unique minimizer. And here is our main theorem. For a convex function on Hadamard manifold, we consider a gradient descent sequence. Then, if the infimum of gradient norm is positive, and as we have seen, this is a sufficient condition for the unboundedness, then first we prove the strong reality, which states that the infimum of gradient norm equals to the superamount of minus of the recession function. And second, we prove that the gradient descent sequence converges to the minimizer of recession function in cone topology. Intuitively, this can be understood as the convergence of direction. For any point y, we consider the direction from y to sequential point x heights. Then, the convergence in cone topology means the convergence of the direction. And third, we also prove that the gradient norm converges to the infimum of the gradient norm on Holder manifold. And these three properties can be expressed as a single equation. Please note that we didn't prove any theoretical convergence rates. We only proved convergence properties. Next, we explain applications of our main theorem. One important thing is that in terms of geometric invariant theory, our gradient descent limit corresponds to a destabilizing one-parameter subgroup. And we also conducted a detailed analysis for unstable operator scaling and show that we can extract simultaneous block triangular form from the gradient descent limit. The Newcomb membership problem is one of the fundamental problems in geometric invariant theory. For a reductive algebraic group and its rational finite dimensional representation, and a given vector in the representation space, the Newcomb membership problem asks to determine whether the origin belongs to the closure of the group orbit or not. And the situations where the origin doesn't belong to the closure are called stable. And one important property is that the unstable case is equivalent to that any homogeneous invariant polynomial of this representation vanishes at V. Then in computer science, it is the complexity of the Newcomb membership problem is an important problem. Indeed, it has been pointed out that many problems in various scientific fields can be solved using Newcomb membership problem. And one approach to this problem is non-commutative optimization. In non-commutative optimization, we minimize this function. And the important things are this function, which is called Kempton's function, is a convex function on Hadamard manifold. And this is unbounded below in unstable case. And the key idea is that in some kinds of actions, we can obtain a lower bound of the optimal value if the function is bounded. So we can determine the boundedness by running the optimization algorithms and checking the function value go beyond the threshold or not. And our situation corresponds to unstable case. And it is known that unstable case is equivalent to that the infimum of gradient norm is positive. And this condition is the identical to the assumption of our main theorem. And it is also known that in this case, there exists a one-parameter subgroup such that the limit of the action to the vector converges to 0. This kind of one-parameter subgroup is called destabilizing. And a destabilizing one-parameter subgroup is a certificate of instability. So we can consider a natural question that for a given unstable input, can we find a destabilizing one-parameter subgroup? Or if we can, is it in polynomial time? And at this moment, it is known that in the left-right action case, we can do it in polynomial time. And for this question, our result implies that the gradient descent limit corresponds to a destabilizing one-parameter subgroup. This is very important because this is a conceptually new approach to find a destabilizing one-parameter subgroup. However, any finite iterations of gradient descent doesn't correspond to a destabilizing one-parameter subgroup. So we need some kind of rounding technique in addition. And at this moment, it is unknown that such a rounding technique is available in general action case. And if this is available, we also have to clarify its complexity. But in the left-right action case, such a rounding technique is proposed. The left-right action is defined by this formula, and this is essentially same as the operator scaling problem. The operator scaling problem is known for the deep connection to the non-commutative Edmonds problem and the Braskamp-Levy inequality. And for Kempton's functions of operator scaling, the most fundamental algorithm is the operator synchron algorithm, along with the gradient descent algorithm. But the limiting behavior of these algorithms are mainly analyzed in the stable case. And the limiting behavior of operator synchron for unstable input is raised as an open problem. Related to that, we prove that the gradient descent limit corresponds to a simultaneous block triangular form. And it is known that in matrix scaling case, the synchron limit corresponds to the essentially same block triangular form. So it is expected that the operator synchron limit is also the simultaneous block triangular form. And an important concept for unstable operator scaling is vanishing subspace. A vanishing subspace is a large zero block which can be obtained by retaking the basis of spaces. A vanishing subspace is a certificate of instability. Indeed, it corresponds to a destabilizing one-parameter subgroup. In recent years, several algorithms to find a vanishing subspace has been proposed. And we proved that the gradient descent limit for unstable operator scaling corresponds to a simultaneous block triangular form. More precisely, let sigma I and tau I be the unitary of the diagonalization of the gradient descent sequence. Then we proved that the sigma I A tau I dagger converges to a simultaneous block triangular form. And in this block triangular form, each maximal zero block corresponds to a maximal vanishing subspace. And this block triangular form can be considered as a vector space generalization of Dawkins-Mendelssohn decomposition, which was originally proposed for bipartite graphs. And it is shown that the structure of divided subspaces are special case of Harder non-significant filtration of Fourier representation. This is our summary. First, we considered the gradient descent for unbounded convex functions on Hadamard manifolds and show that the strong duality holds, and it is achieved at the limit of gradient descent. We also showed that the gradient descent converges to the minimizer of a session function, which is at the infinity of the original manifold. And these results are applicable to the geometric invariant theory. And especially, the gradient descent limit corresponds to a destabilizing one-parameter subgroup. And in the operator scaling case, the gradient descent limit is a simultaneous block triangular form. For future works, we would like to obtain some kinds of convergence rates and some kinds of rounding technique for general actions. And as our final message, we would like to tell you that unbounded convex optimization is a meaningful problem, and it's a new possibility to find a destabilizing one-parameter subgroup in general action case. Here are the references. Thank you for watching.